Given that this week you have a greater workload with the assignment and the test, I decided to make this lecture a bit simpler than average, and then we have more time to discuss other issues during the synchronous session. So this time I'm going to talk about a specific type of models that we may want to adjust to our data that represent systems that evolve over time. And usually these are modeled with differential equations. You may have differential equations for other things not involving time, but more often the case in practice, this is used for systems that evolve over time. So we're going to see how we can solve these differential equations in order to obtain the actual values we're trying to predict, and then how to fit these. Finally, we're going to look at evaluating the fit, but from a different perspective than what we've been seeing so far. So previously we saw the fit with our model as either just a tool for visualization or something that allows to predict new values. When we did, for example, regressions, and we used the training, validation, test in order to evaluate how well the curve we were fitting was useful for us. In this case, we may want to fit this model not to try to predict new values, but to try to understand some process that is occurring. And so we want to look at the parameters of the models that describe something we're trying to find. So in this case, evaluating the fit is not so much trying to see how well we can predict something new, because we're not trying to do that, but how well the model is describing the data that we have. Okay, so I'm going to focus on this example. This is just an example of a differential model, but this is a model used in economics, the BAS model, Best Diffusion Model, that tries to capture how a new product is adopted by the market, so by buyers. So suppose some new product is invented, a computer game, the iPhone, the VCR, something like that, and BAS proposed dividing the users or the buyers of this product into people who are affected by two different factors. So this innovation, which is people see the ad or try to want to experiment this new product and so on. So this is more or less a constant factor that is driving the adoption of the product. So these are the innovators, and this is the innovation coefficient. And then you have the imitation, which is what happens when people are adopting the product because they see that others are also using the product. So someone they know or someone they see on the street or something like that. So this factor will influence the adoption of the product in proportion to how much of the product has already been adopted. So the idea here is that this f function, f of t, is telling us how much of the total market for the product has already been covered. So how much, what is the fraction of adoption relative to that maximum, hypothetical maximum. And we know that so BAS proposed for this model that the variation in adoption, so how much is adopted at each time, which is the derivative of this fraction. So how much the fraction of adoption is changing over time, as a proportion of how much there is still left in the market capacity. So this is 1 minus ft, because this is the difference between the fraction that has already been adopted and how much the market can still sustain. So this variation in proportion to how much the market can still bear is composed of these two factors. So a constant factor, a constant relative to this proportion, of course, but this constant factor is that motivated by innovation. People just want to try the product, and a factor that is proportional to how many people already using the product. So this is the imitation factor, because if many people are using, then other people also want to use it. Okay, so this is the attempt to describe how new products are adopted. We can convert this equation, so we put this denominator here on the other side. So basically, the derivative of the fraction that is adopted over time, this ft is the fraction adopted at time t, f line t is the derivative of this function with respect to t. So the derivative is this expression here, where p is the innovation coefficient. So people wanting to try the product just because they see the ads or because they think it might be fun or something like that. Q is the imitation coefficient, so people wanting to try the product because they see others using the product, and the effect here will be proportional to the fraction of adoption already. And this 1 minus ft is what is left of the market capacity, so the fraction that is still left to adopt. And this is basically the expression that we can use. We know the derivative as a function of the actual these coefficients and the fraction that has been adopted. But note that we don't have a direct way of computing the fraction that has been adopted. We just have an expression for computing the derivative. So we need to solve this problem by integration. Okay? So let's see a particular example. We have this file iphone.txt, which has the cumulative sales of iPhones in millions from the third quarter of 2007 through 2018. So we have this in a text file, and we can just load the data and look at the data. This is always a good idea. So this is nothing new for you. NumPy, Matplotlib. This is just my fixation with Seaborn. I don't like the default look of pyplot. So we load the data, we create a figure, and we plot it. And you see this curve here, which is the cumulative sales and how they are increasing over time. So now we want to try to fit the BAS model here and try to look at these parameters, because the idea is not that we're going to use the BAS model to predict things. Well, in theory we could, but we don't know exactly how good our predictions will be because conditions may change. But one interesting thing here is that this model is actually trying to capture some parameters that mean things. So this P would be the innovation coefficient, could be influenced by things like advertising and so on. And this Q is the imitation. It's more like word of mouth, and people see other people using iPhones and so on. So if we could measure these different effects, we would have an idea of what is driving the adoption of the iPhone. So this would be the purpose for this kind of fit. Okay, so what we need to do here is we need to compute this ft, because this what we are seeing here, the cumulative sales, is the total adoption of the iPhone so far. But we need to figure out how much this is in fraction, as a fraction of the total market capacity for the iPhones, and then we need to be able to compute that, to adjust it to the data in order to find those parameters. So what we need here is some way of integrating this differential equation, which gives us the derivative of f, but we need to integrate this in order to find the actual f. Now the problem is that this is also dependent on f, but we can do this numerically with this doing this step by step if we start with some initial value of f. So if we start at 0 before the product is adopted, and then we can compute this over time and integrate this function. So this is basically an initial value problem that we can use to integrate ordinary differential equations, which are these differential equations that depend on one variable. And we can do this with SciPy in the integrate module. You have this solve initial value problems, or solve IVP function that you can use for this. So basically, if you import this function and use help to see how the function works, or you can look on the internet, the documentation, you see that this function will receive one function, which is the derivative function, a time span where you want to do the integration, the values for the initial values to predict to obtain here. Basically, this is a list of values because you can use this to solve a system of ordinary differential equations. In our case, our system is only one equation, but we could have a number of equations. Which time steps you need to evaluate, and so on. So there are many options here. So basically, we can, if we write the function for the derivative, we can use this one to integrate given some initial value. In our case, the initial value will be 0. This is the adoption of the product at the beginning of when we're counting the time, and then we obtain the integral of that derivative, which is the function we are interested in. Okay, so we can let's write the derivative function. The derivative must have this these arguments, so it must receive the variable over which we are integrating first. This is time t, and the value of the integral so far. So this allows us to compute the derivative here. So this this function, we can assume, for example, a p of 0.5 and a q of 0.2. We can write this here. So this is the expression of the derivative. We can just write it here. And this is the computation of the derivative. We return the derivative of f. And now we compute f by using solve IVP over this function for a time span between 0 and 10 time units. So this is arbitrary here, just to see the result. This is the initial value of f. We have to put it as a list because this is, in general, you can use this for a number of ordinary differential equations. In that case, this will be an array which will give you the initial value for each of your differential equations, and it will be then integrated and accumulate the value there. And now what are the time steps we want to evaluate? So if we are computing between 0 and 10 in time units, let's evaluate 100 points uniformly distributed between 0 and 10. So this is just to draw the line, and then we create a figure and plot. Now, since this can be used for a number of differential equations, the result here as this y value, this is the result of the integration, but this is a matrix with as many rows as the equations that you want, and the number of equations is determined by this array here. So in our case, we are only using one differential equation, so we only have one initial value here, and we only have one integration, one series of values with the integral over here. So this is the first row of the y attribute. If you don't put this here, then plot will complain because it will not understand why you have so many values on the first row there. So we are just selecting the values on the first row, and this is the result of the integration. So if you use an innovation factor of 0.5 and an imitation factor of 0.2, you get a curve like this. This is total adoption, and this is time. But this is just to experiment, so an artificial example. We can change the parameters, for example, so let's put a lot of imitation and less innovation, and you see that now the curve is like this because it starts to become important. The more people adopt the product, then the more people are adopting the product because there is more imitation, and so we get a curve more like this with an S shape. Okay, so this is the basic mechanism for solving the differential equation and obtaining the value of the fraction of adoption over time based on this differential equation. But now we need to adjust these parameters. We cannot make these parameters up. We want to adjust them so that the curve fits our data. And another thing that we need to think is that this is working with fractions of adoption. but our data has actual sales. So these are the sales in millions of iPhones, and we need some way to convert this into a fraction by assuming some value for the market cap. So we need to have these three parameters. We need the P and the Q, which are the parameters for the fraction of adoption, but we also need this market capacity value M, which will tell us what actual number of iPhone sales corresponds to a fraction of 1 when the market is saturated with iPhones. And we're going to fit the three parameters, adjust the three parameters in order to fit the curve as well as possible to these data. Okay, so to do this, we need to use a Python trick here, because you see that in order to use solve IVP to integrate our differential equations, we need to write a function for the derivative that receives as arguments the time and the value of the integral so far. So we cannot give this function these parameters that we need, the P and the Q, because it has to have this format in order to fit into the solve IVP function. However, Python allows us to do this easily because we can use a nested function. So this is function closure with Python, because if you create a function inside another function, the nested function can see the variables, the local variables of the function that is wrapping it. So if we create this function called create derivative that receives the P and Q, this function creates a new function object called derivBus, for example, that can use the P and Q that was supplied to this outer function. But now it returns this one as an object, and the arguments for the derivBus function are only the ones we need, so T and F here. So doing this, we can create a derivative function, the equivalent of this one here, but we created using this wrapper function that receives the P and the Q. So this one creates a local object called derivBus here, but then it returns that object. So here we have this new function that receives only these arguments, but can see the P and Q that we supplied to the outer function. So now we can solve the initial value problem with this object function, this object of a function that can use these parameters that we specified here. So using this wrapper, we can adjust the parameters as we want and then call the solver to integrate this. So let's see what we need to do the minimization. So first we need to make the prediction. So remember that when we are doing the minimization, we want to minimize a measure of error. So generally we use the mean quadratic error because we are assuming normally distributed error on the values we're trying to predict. And so we first need the prediction in order to compare with the data and compute that loss function, that error function. So we'll create this prediction function, so predict using the Bus model. We receive a vector of parameters, which are these three that we want to use, P, Q, and M. So we receive a tuple with the three parameters that we can unpack here so we don't make mistakes. And we also receive the time steps where we want our predictions. So this is the number of time steps. We'll assume that we want to predict for every time step. Note that time here is arbitrary. It can be days, it can be years. In this case, for example, with iPhones, it's quarters. We are taking the total number of sales for each period of 3 months, after each period of 3 months. So we have these 4 points per year. But we'll just consider in abstract to be a time unit. Okay. So the prediction, the way this works is we get these parameters, we unpack these here, we create the derivative function using the P and Q, we solve the initial value problem. So if we use this P and this Q value, we have this integration of our differential equation. So we start at 0, we integrate between time 0 and time corresponding to the number of time steps that we want, and then we evaluate over all these time steps, so 0, 1, 2, and so on. Actually, we are computing a bit more time than what we're evaluating, because this stops at t steps minus 1, but that's not very important. Okay, so now we have the solution here, which tells us the fraction of adoption at each time, which we obtain by integrating that differential equation. And now we need to convert that into actual number of iPhone sales. So we use the third parameter. The third parameter is the market cap, and we multiply the fraction by the market cap, and we have the total number of iPhone sales. So this is how we predict the number of sales based on this BAS model given the parameters. And now we create the loss function, which is the error function that we're going to minimize. So we have the parameters and the data. We predict the values, the sales, the total sales at each point in time using these parameters. And we want as many points as we have in the data, so 1 for time 0, 1, and so on. So as many points as we have in our data. And the error is simply the mean of the quadratic difference, of the square of the differences between the prediction and the data, and we return the error. So this is just the basic quadratic error function that we've been using. The only difference is now that the prediction also involves doing this integration, because we have a differential model and we cannot do the prediction immediately. Okay, so now we adjust the parameters. We're going to import the minimize function from SciPy. We're going to compute the fit by minimizing this loss function here, which calls the prediction. And we start with an initial guess of 0.5 and 0.5 for the P and the Q, and the maximum value in data as the initial guess of the market cap. Of course, these are not the actual values that we end up at the end, but this is just the initial point for starting the minimization. The additional arguments for the function to minimize is the data, because the function to minimize will receive the parameters and the data. And we also set reasonable bounds for our values. So the P and Q coefficients should be between 0 and 1, and the market cap should be between 0 and whatever the minimization needs, so we don't put an upper bound here. So the bounds argument works like this. You give an array of tuples with each tuple corresponding to one of the variables you're trying to optimize, and each tuple contains the minimum and maximum value. And if you want to omit one of the bounds, you just put a none instead of a value. So we do this for minimizing. We obtain here in the fit, this X attribute has the parameters that we found. And now we can do the predictions with these parameters for all our data and plot, and also check the parameters. So the innovation is P, PQM are the three parameters. And we can see that in this case, innovation is a very small contribution, and imitation contributes a lot more than innovation. So basically, and we can also estimate the total number of iPhones that will be sold when we reach the market capacity. So when the fraction reaches 1. And this is the curve. So this is the data, and this is the predicted curve here. So you see this kind of curve is indicative of this difference where innovation is much lower than imitation. So this means, at least if the model is correct, it means that people tend to buy iPhones because other people also have iPhones. And this seems to be the strongest driving force behind the adoption of iPhones. Okay, so now that we have the model and we can interpret the results, we also need to ask how good is the fit, because note that we are assuming these equations and parameters to try to understand what is happening, what is driving the adoption of iPhones, but we must also try to evaluate if our model is actually able to fit the data correctly. So if we want to estimate how good a predictive model is, which is what we've been trying to do in the last sessions when we were looking at validation error and test error, so we want to look outside the training set to see how well our predictions generalize outside the data we use to fit the model. But this is not all that we do with models. Sometimes we just want to fit the model in order to understand the data that we already have. So in this case, looking at these imitation and innovation parameters, the market cap and so on. And then we want to check if the fit is good. So we don't particularly care about predicting new values because we don't have those extra values also to check, but we want to see if we are capturing something about the data. We're going to see a bit more on this. I'm going to talk a bit more on these differences of how to use the model next week after we look at cross-validation. But in this case, I will just quickly go through two things that we can do, or three things that we can do to try to evaluate the model. So one is to use the same thing that we are trying to minimize. So we are minimizing the mean square error. So this is what we have here in the loss function. We subtract all the predictions from all the corresponding data, we square that, and we compute the mean. So this is what we're trying to minimize to fit the model. Now, this is also a hint for the assignment that you're doing, because you have a question on that. The problem with this measure is that the units are a bit strange. So if we compute the mean of the square of the difference between the predicted value in number of sales and the actual value in number of sales will also be a number of sales, but the square of the number of sales is something that is strange. So in iPhone squared is a strange unit. When we take the root of the this squared error, so if we take the mean of the squared error, which is this part here, this gives us a unit that is the square of the units we are using in our problem. But when we take the root of that, now we have the actual units that we were using. So this root mean square error, or root mean square deviation, it's also another name that is used, is simply the root of the mean quadratic error that we've been using, and has this advantage that it has the same units as what we are measuring. It's also the standard deviation for the residual. So basically we are doing this if this is an unbiased estimate and so on, we have basically a standard deviation here. But this is useful because it gives us an idea of how much or how well or close our model is fitting the data. So in this case, the RMSD is about 13 million iPhones. This is the root of the mean of the quadratic error that we are doing, which is pretty good because there is 1,400 million iPhones here in our data approximately. So we are just making a mistake. The standard deviation here of our errors is 13, so this is pretty good. So this is one way we can judge how well our model is fitting the data. Another thing that is useful is to look at the distribution of the residuals. So remember that the residuals are these differences here between what we predict and what the actual data is. And we can look at how they are distributed over our series. So we can see that in the beginning, they tend to be mostly negative, the residuals. So you see here, and you can see here, that the values we are predicting tend to overestimate the actual sales. So the residuals tend to be all negative. We are predicting higher than the actual data is. And but eventually, when we get to a large enough number, then the residuals seem to be just spread out at random, which is our assumption when we are doing the fit. So remember that we are using this uh, minimizing the quadratic error, because we assume that these residuals, so the difference between what we predict and the actual data, will be affected by this kind of random noise with a normal distribution. So it seems not to hold very well at the beginning, but then it seems to be fairly good, because it seems to be randomly distributed there. So this is another way that you can look at looking at the residuals. You can check if there are parts of your model that seem not to be fitting well, or if there is something suspicious in this case. Okay, so since we are assuming the residuals are normally distributed, we can also try to check if this is true. So we are assuming that there is some normally distributed error, and we are approximating our curve to the data, minimizing the quadratic error, because in those conditions this corresponds to the maximum likelihood solution. This is what we saw in the beginning of these lectures on regression. So we can test that, and one easy way of testing that is with a probability plot. There are other ways. You can use histograms to see if it's approximately normal and so on, but the probability plot will show you the plot of your data against the corresponding quantile of each point. So you take in this case the normal distribution, and what you have, I can show you first like this, is this is what would be the theoretical value in the distribution, so the quantiles for the theoretic distribution when we normalize this. So we assume that this was all standardized to a normal distribution, and this is how we would expect our values to be distributed. So over on these places on the x-axis, and on the y-axis is the actual values of our residuals. So if this is exactly in a straight line, then our values are distributed exactly in a normal distribution. We have a slight deviation, especially here at the ends, because the range of our values seems to be a bit shorter than an actual normal distribution would expect. Then we have a bit of a deviation here, but overall, when we plot this, we have an R value of 0.98. So this is a pretty good straight line in this case. So the easy way of doing this is using the probplot function in SciPy stats, and what this function returns is two tuples. One with the arrays, the array of the quantiles in the distribution that we choose. So in this case, I'm choosing a normal distribution here. And the second array is the observations sorted. So we have everything sorted in increasing order, and we have the two arrays with the quantiles and the observations. So this is the first tuple. The second tuple has the slope, intercept, and R of this linear regression that you see here, the linear regression of the values of our, in this case, our residuals, our observations, with respect to the quantiles here on the distribution. If you want, this probplot function can also generate a plot. You just need to give it something to plot into. So either the PLT, so the pie plot, or the set of axes that we are getting from the figure. So here we created a figure. Actually, this is not necessary. You can just do like this, and then the GCA is get current axis. So we are getting the axis of this figure that we created, and since probplot receives this argument, it will generate the plot on those axes. So basically all you need to do is this, and you can observe how the values that we have on the residuals compare with the corresponding quantiles, if assuming a uniform distribution. So the more this approaches a straight line, the more similar the distribution of values we have is to a uniform distribution. Sorry, a normal distribution, not uniform. Okay, so this is these are just some ideas of using the residuals to evaluate how good the fit is. We're also going to see another use of the residuals next week when we look at residual bootstrapping. But for now, the exercises that you have are very simple because you are doing the assignment this week. So we're going to lighten the load a bit on this. You just have two other data files. So internet, this has the number of internet users in millions for every year between 1995 and 2015. And this arc.txt has the total sales of Ark Survival Evolved. This is a computer game for every day from June 1, 2015. So what the exercise is for each of these cases, you're going to use the BAS model and check if the BAS model describes this data series well. So basically, you have to do this sort of thing, measure the RMSD, check the distribution of the residuals, check if not only how the residuals are scattered here along the time, but also if the distribution is approximately normal, which is what we are assuming when we are doing this fit. And so it should be something like this. And also, once you fit the data, you can try to check with the parameters that you have if you think that more people are adopting these, either the internet or buying the computer game because they see others adopt them, so the imitation factor, or due to something like advertising or because they want to try out or something like that. So basically, you're just going to apply the same thing that we saw here, applied to the iPhone sales, and apply this to the two data sets. Okay, so to sum up, what we saw here was just a different kind of model that we can try to adjust to our data, which the main purpose in this case was not so much to help with visualization or to predict new values, but actually this is also a different application of this kind of adjustment, of adjusting the models, in which we want to fit the model because we want to understand what's happening to the data. So these models describe, in this case, the BAS model describes what is happening, but it's also a differential model. So we don't have a direct way of computing the values that we are trying to adjust to. We have a differential equation, and we need that extra step of integrating the differential equations. There are many examples of this kind of models. For example, in epidemiology, you have models that describe how the disease is spreading. In physics, you have lots of differential models for things like heat transfer and things like that. So this happens in many fields where you can describe how things evolve over time by looking at the change over time, but then you need to integrate that change, the derivative, in order to get the actual values. But basically, it's the same recipe. We're trying to minimize an error function to adjust the parameters. We just have that extra step of having to integrate the differential equations in order to get the values for the predictions. And then we also saw this problem of checking how well the model is fitting the data, but not with the intent of predicting new values or things like that, just to see if this is the correct model for that data. Because usually when we are doing things this way, when we have these models that try to describe what is happening behind the data, so to speak, we need to see if the models are actually correct for the data that we have. So some things that you can do, you can use root mean square deviation. So basically you take the root of the quadratic error, and in that way you are converting this into the same units that you're using, so it's easy for comparison. And also another thing to do is to look at the distribution of residuals to see if there is something suspicious, some part of your data series where the model is not fitting well, or if the residuals are not well distributed, and so forth. Okay, so that's it for this week. This lecture was a bit lighter, but then we'll talk on the synchronous session to see if you have questions about this or the assignment. And next week we'll start moving on with cross-validation and looking, giving a bit more of an overview of these different types of models and applications, and also using residuals to try to estimate the uncertainty on these parameters.